This is Cambridge IGCSE, paper 6, alternative to practical for chemistry from February-March 2021. Question number 1. Silver chloride is an ionic compound and is insoluble in water. Molten silver chloride breaks down during electrolysis. The products are chlorine and silver. Chlorine gas is soluble in water and toxic. A student suggests using the apparatus shown to break down silver chloride. A. Draw an arrow on the diagram to show where heat must be applied so that the silver chloride can break down. So you need to heat the silver chloride, which is here. Heat it from the bottom. All right, moving on to B. Complete the diagram to show how chlorine gas can be collected and the volume of the chlorine measured. Label any apparatus you have drawn. So how can we measure the volume of chlorine measured, which is a gas? You need to use a gas syringe. So let's draw a gas syringe real quick. So you can draw the frame, and then the scale is ready. Allow me to redraw that. I'm not exactly an expert in drawing using the iPad. So with that, you draw the scale. Right, just a rough estimation. Then with the movable part, oops. Yep, and then we can draw the head of the gas syringe. So this is a gas syringe. Right, so you can check Google for how you can draw a gas syringe. There's many ways to draw it as long as it's visibly a syringe. Okay, with skills ready. So with that said, okay, that's a gas syringe. Let's look at how the marks are awarded. The first mark is that the gas syringe is in a horizontal orientation. Okay, it's connected to the delivery tube here. Okay, and then the next mark is that you can have the graduation shown or you label this thing as gas syringe. Okay, then you should be able to get 2 marks full. Moving on to C, give 2 observations that are made as the silver chloride breaks down. Well, as mentioned in the question, silver chloride breaks down to form chlorine and silver. So the observations will be related to these 2 products. Right. So you may mention that, well, chlorine gas is formed, but don't mention the name because it's about observation. It's what you can see. So chlorine gas is a greenish, yellowish green gas. Right. And then meanwhile, you can talk about the silver that is formed. As mentioned, don't mention the name of the chemicals. What you see there's a shiny deposits. Okay, you talk about shiny liquid, shiny metal, shiny solid, shiny deposits. Okay, other than that, right, because this essentially is in molten state, so you will see the bubbles, the efflorescence that occurs due to the chlorine gas form. All right, so you will see like efflorescence here, okay, formed at the essentially that's due to the chlorine gas that is formed. Right, moving on to D, the person doing the experiment followed all normal laboratory safety rules. State 1 additional safety precaution that should be taken when doing this experiment. Give a reason for your answer. Well, you are essentially dealing with a creepy, green, toxic gas. Right, so how should you operate this experiment? You should definitely use maybe you can use fume cupboard. Okay, operate this experiment under a fume cupboard, or you can do this experiment in a well-ventilated space. Okay, why? Because Chlorine is toxic. It's bad for you. It can kill you if you're not being careful enough. All right, moving on to E. Suggest one reason why zinc is not a suitable material to use as the electrodes. Now, why is zinc not used as the electrodes? The setup is to break down silver chloride. You do want to introduce new things inside this whole setup. Right, zinc is an active electrode, which means that it will actually affect this reaction. How does it affect this reaction? If we choose to use zinc, the chlorine gas will actually react with the zinc. So as a result, the outcomes get affected. You don't want it to happen. Okay, so in paper 4, remember that zinc is an active electrode, but in the context of paper 6, you should just mention that now zinc is able to chlorine form. All right, so with that said, let's look at look at F. The chlorine gas was bubbled into an aqueous solution of a sodium salt. The color of the solution changed from colorless to orange. Identify the sodium salt and explain what has happened to cause the color change. All right, you see this? Okay, in IGCSE syllabus, what are the solutions that look orange? Other than indicators, the other one is bromine, right? Bromine is brown, like reddish brown, orange brown in color. So what is occurring here? If you know your theory well, this colorless solution is actually a bromide solution. Okay, essentially bromide is colorless, but when it turns into bromine, it becomes brown. Right? Of course, depending on the state itself. Now, so what is occurring here? Halogen displacement reaction. Essentially, chlorine, which is a stronger, more reactive substance than bromine, leads to chlorine displacing it, okay, stealing sodium from the bromide ions. All right, and as a result, it forms sodium chloride and bromine is disqualified. It gets kicked away. All right, so with that said, the sodium salt is bromide salt, right? Sodium bromide. So the explanation here is chlorine is more reactive than bromine. Or you may also mention that bromine is displaced by chlorine. All right, you can also talk about chlorine essentially oxidizes bromide. Right, if you see closely, this is actually an oxidation. Like this is an oxidation reaction. Okay, essentially chlorine is acting like an oxidizing agent here, depending on which one you prefer. Okay, so moving on to the next question. 2. A student investigated the reaction between aqueous potassium hydroxide and 2 different aqueous solutions of hydrochloric acid labeled solution A and solution B. 2 experiments were done. A. Experiment 1. A burette was filled with solution A. Some of solution A was run out of the burette so that the level of solution A was on the burette scale. A measuring cylinder was used to measure 25 cm3 of aqueous potassium hydroxide. The aqueous potassium hydroxide was poured into a conical flask. So this is potassium hydroxide. Okay, the burette contains hydrochloric acid. The conical flask contains potassium hydroxide. And then 5 drops of metal orange indicator were added to the conical flask. Solution A was added slowly from the burette to the conical flask, while the flask was swirled until the solution just changed color. Use the burette diagrams to complete the table for experiment 1. So let's read it. The final reading is 17.9. And then the initial burette reading is 8.0. So the volume of solution A added is actually just 17.9 minus 8.0. That gives you 9.9 cm cube. All right. Experiment 2. The conical flask was emptied and rinsed with distilled water. The burette was emptied and rinsed with distilled water as well. The burette was rinsed with solution B. The burette was filled with solution B. Some of solution B was run out of the burette so that the level of solution B was on the burette scale. A measuring cylinder was used to measure 25 cm cube of the aqueous potassium hydroxide. The aqueous potassium hydroxide was poured into the conical flask. 5 drops of metal orange indicator were added to the conical flask. Solution B was added slowly from the burette to the conical flask, while the flask was swirled until the solution just changed color. It's the exact same setup, right? But this time you're using B in the burette. So let's see. Use the burette diagrams to complete the table for experiment 2. Let's read it. The final reading is 27.3. The initial burette reading is 7.5. Hence, the volume of solution B added is 19.8 cubic centimeters. All right, state the color change observed in the conical flask at the endpoint in experiment 2. So metal orange indicator, if you remember its color, right? The color of metal orange in an alkali solution is actually yellow, right? Metal orange is yellow when it's in an alkali medium. And then when it turns neutral, you're doing neutralization in this reaction. It will change to orange. All right, moving on to C. Before starting the titration in experiment 2, the conical flask was rinsed with water. Explain why the conical flask was rinsed with water. Well, to remove the residues from experiment 1. All right, moving on to 2. The conical flask was not then rinsed with aqueous potassium hydroxide. State how rinsing the conical flask with aqueous potassium hydroxide would change the volume of solution B needed. Explain your answer. As you can see, we do not do that because it will actually affect the volume of solution B needed. Right. So why are we not doing that? You see, the logic here is you are, well, if you choose to rinse it with potassium hydroxide, you are essentially leaving a little bit more, a little bit extra potassium hydroxide in the conical flask. Right, supposedly you just want to measure 25 cm cube, but just now you rinse it with potassium hydroxide. There's residues of potassium hydroxide in the conical flask in the beginning. Maybe it's 0.1, maybe 0.2, and then you add 25. So you're not exactly titrating 25. Maybe you're titrating like 25.1, 25.2. So it will actually affect the results. Okay, so you do not want it to happen. So, but if you choose to rinse it with potassium hydroxide, it means that you need more acid to titrate. Right, so it will increase. Why? Because there is more potassium hydroxide in the conical flask. Okay, you are adding 25 on top of the residue, which affects the result. All right, moving on to D. Deduce which aqueous solution of hydrochloric acid, A or B, was more concentrated. Explain your answer. Now, let's see. For A, we're using 9.9 cm cube of acid. In B, we're using 19.8 cm cube of the acid. Let's write it down. So A and B are acids, and this one has less, this one has more. So if you mean that the concentration of A is way stronger, it's way higher, right? So solution A is more concentrated. Why? Because less volume is required to titrate potassium hydroxide. All right, compared to B. Moving on to 2, deduce how many times more concentrated this solution of hydrochloric acid was than the other solution of hydrochloric acid. Well, so in terms of concentration, A is more concentrated, and then we see the volume decreases by half, which means that the concentration is double of B, right? It's twice. Okay, twice as concentrated as B. Moving on to the next question. E, explain why experiment 1 and experiment 2 should be repeated. Well, as to, there's actually two main reasons why we do that. One is that it allows us to spot anomalous results, weird results. Other than that, it also improves the accuracy by allowing us to find an average. Okay, or you should say that it is a mean. Okay, moving on to F, deduce the volume of solution B required if experiment 2 is carried out with 50 cm cube of aqueous potassium hydroxide. So, based on the question, we are titrating 25 cm cube, and then we need 19.8. So, if we are using double the amount of alkali, it means that it will be double of the acid used. So you have to take 19.8 multiplied by 2. So that gives you 39.6. So the volume is 39.6 cubic centimeters. Right? So it's 2 marks. The first mark is your value. The second mark is your unit. Oops, my bad. Oh yeah, it is cubic centimeters. This is volume. All right. G. Describe one change that could be made to the apparatus to improve the accuracy of the results. Now, if you notice that this question is using measuring cylinder. Now, despite it is easier to use a measuring cylinder, it is not of the best accuracy. It's better for you to use a volumetric pipette. To measure the volume of potassium hydroxide. Lastly, H. Describe what effect using a larger conical flask would have on the result obtained. No effects, right? There will be no effect on the results. Right? It doesn't matter whether you use a bigger bottle or smaller bottle, it doesn't matter. Right? Bigger flask, smaller flask, not exactly a big issue. All right, moving on to number 3. Two solids, solid C and solid D, were analyzed. Tests were done on each solid. So in terms of solid C, tests were carried out and the following observations were made. The test is, for number 1, a flame test was carried out on solid C, and then we see a red flame. When we see the word red flame, we should think of lithium ions. Okay, this flame test. Lithium ions exhibit red color, okay, under flame test. Then in terms of solid C, was dissolved in distilled water to produce solution C. And then test 2 is about 5 cubic centimeters of aqueous sodium hydroxide was added to solution C. So this is cation test, but we see that there is no change. All right, so which means that it's neither of the list that you remember from under the cation test table. Let's move on to 3 anyway. A piece of aluminium foil was added to the mixture formed in test 2. The mixture was warmed gently and any gas produced was tested. Now, whenever you see aluminium and warm gently, gas tested, if there's any gas that is produced, you should think of nitrate ions. And then the gas that is formed will be ammonia. Okay, you can actually see the observation, which also gives you a clue. You see, the only gas in IGCSE syllabus that is alkali is ammonia. Right, so you can pretty much guess what's the ion form, okay, that leads to the formation of ammonia. It will be a nitrogen-containing ion, which is either ammonium or nitrate. And then in this case, it's nitrate. All right, so name the gas that turned the damn red litmus paper blue in test 3. That will be ammonia. Right, B, identify solid C. So what do we see here? It's a lithium nitrate. All right, moving on to the next question. Test on solid D. Solid D was aluminium sulfate. Complete the expected observations. Solid D was dissolved in water to form solution D. Solution D was divided into 4 approximately equal portions in 4 test tubes. C, aqueous sodium hydroxide was added dropwise and then in excess to the first portion of solution D. As mentioned, sodium hydroxide is for cation test. So it's responding to the aluminium ion. So how does aluminium ion react with sodium hydroxide solution? It forms a white precipitate. And this white precipitate actually dissolves in excess. All right, so that's the feature of aluminium ions in response to cation test. Moving on to D, aqueous ammonia was added dropwise and then in excess to the second portion of solution D. What's the observation here? So this is another kind of cation test. Okay, cation test, there are 2 ways. Either you use sodium hydroxide or you use ammonia. So in the case of ammonia, it is still white precipitate that is formed. Okay, because aluminium is not a transition element. It won't form like fancy colors. Okay, it won't form like, like green, blue, like in transition elements. Okay, because aluminium is a non-transition element, so it should be pretty boring. It should be just white in color. However, in this case, right, the solubility differs. In ammonia, actually, it does not dissolve in excess. Okay, if you don't remember this part, you can have a look at cation test table in your syllabus. Moving on to E, about 1 cm cube of dilute nitric acid and a few drops of aqueous silver nitrate were added to the third portion of solution D. Whenever you see the word silver nitrate in aqueous form, the silver ions are the main character here. Silver ions react positively with halide ions to form silver halides, which are precipitates. Now, the question here is there any halide that is present? Any bromides, any iodides, any chlorides? No. So it will have no observation. Or should I say no change? All right, F. About 1 cm cube of dilute nitric acid and a few drops of aqueous barium nitrate were added to the fourth portion of solution D. Now, this time the main character here is barium nitrate, and then the actual main character is the barium ion. Barium ion reacts positively with sulfate ions. They are besties with sulfate ions to form similarly barium sulfate, which is a precipitate. So, is there sulfate present? Absolutely. So, you will see a white precipitate in this reaction. All right, moving on to number 4. All concrete contains calcium carbonate. Calcium carbonate reacts with dilute hydrochloric acid. Plan an investigation to find which of 2 lumps of concrete contains the larger percentage of calcium carbonate. Your plan should include how you will use your results to determine which one of the 2 lumps has the larger percentage of calcium carbonate. You have access to all common laboratory materials and a supply of dilute hydrochloric acid. Now, in experiment planning, it's best for you to identify the variables first. Right? What is the experiment about? So you have to find out the dependent variable, the independent variable, and also the control variables. So what is this question about? It wants you to plan an investigation to find which 2 lumps of concrete contain larger percentage of calcium carbonate. So your dependent variable should lead to this conclusion. Now, you can think of maybe mass, right? Mass, okay, percentage by mass. Okay, hence maybe you can plan your experiments around the idea of mass. Okay, let's talk about control for a second. So means that you shouldn't care about, well, you shouldn't care about the other variables should be kept controlled, like kept constant. So for example, the volume of hydrochloric acid use, and then maybe you can talk about, to be fair, you use the same mass of concrete. Right, and many more. Okay, so the dependent variable is more of the percentage by mass. So you can maybe think of maybe the final mass after reaction, right? Mass after reaction. Okay, this is not final, yeah. This is just a rough idea for us to clear our mind and then build an experiment out of it. Independent variable should be the 2 lumps of concrete. So to be fair, you should use the same mass of both concretes. All right, so let's plan our experiment around it. Well, first of all, you can mention that, okay, I'm going to use, let's say, the same mass of concrete. Because you want to be fair. Let's say you are using 10 grams each. Right. And then you put them into the same volume of dilute hydrochloric acid. Right. So it's essentially taking test tubes and then put the acids of the same volume and then same concentration, and then you place the concrete in. What else? Make sure that your hydrochloric acid is in excess so that you can ensure that all the concretes have reacted, or else it will definitely affect your results. Okay, HCl in excess. Okay, so how can we know which one has a larger percentage of calcium carbonate? Your focus can be either on the reactants or the products, right? So let's say you're using 10 grams, okay? 10 grams. Two situations, right? The one that has more calcium carbonate will actually have a greater reduction in mass, right? Let's say 8 grams. This 10 grams of concrete A contains 8 grams of calcium carbonate, which means that your remainder, okay, will be 2 grams. And then if let's say concrete B has less calcium carbonate in it, let's say we talk about 5 grams, the remainder will be 5 grams. These are unreacted solids. So you can pretty much set up a before and after the reaction situation, right? So before versus after. All right, so before you measure 10 grams for each, 10 grams each, and then after you are essentially dissolving in acid, right? So you need to take out the remainder. How do you do that? Solid from aqueous solutions, filter it, followed by filtration, dry it, right? Wash and dry the residue. And then next you can weigh, right? You can measure the mass of the residue. Okay, and then how does that lead to your conclusion? So as you can see from the example I gave just now, the one with the lower mass remaining, that will be having the highest percentage of calcium carbonate. Okay, otherwise you can look at, well, from what I see from this question, I feel like mass is easier to be, well, it's easier for you to write the setup using mass, although there are other variables they can look at. Okay, from the answer scheme, you can actually also look at carbon dioxide, right? Carbon dioxide gas form. Okay, if let's say this concrete contains more calcium carbonate, it means that more carbon dioxide is going to form. So you can use a gas gauge to know that. Okay, so you can talk about more carbon dioxide form, and then essentially measure both of them and then lead that to your conclusion. Okay, many ways to write about this question. Other than that, you can talk about the mass of the new product. But this is also another product that can measure. Essentially, you just need to dry it, evaporate it to dry, and then see which one produce more. Same concept as the carbon dioxide gas. So many ways to write this, as long as you give me 6 points, at least 6 points, okay? If you want to score full marks, please give me maybe 7, 8 points, just to be safe. Okay, so I concepts correct, and then you write sufficient points, you'll be able to get 6 marks full. All right, so that's all for the discussion of this paper. Thank you so much for watching. I hope that it helps you in your examination, and all the best to you in your examinations, and I'll see you in the next one.